Hello, this is Mike from Applied Motion Products. Welcome to part 4 of our video tutorial series showing how to get up and running with an Applied Motion Products Ethernet IP integrated motor in Studio 5000. In this installment, we'll talk about setting up and using the TruCount Absolute Encoder. We've got a whole webinar on the Absolute Encoder up on our YouTube channel on demand, so if you're interested in tech specs, etc., I'd encourage you to watch that first. Like the last video on hard stop homing, a lot of this video isn't only applicable to Ethernet IP, as we'll cover setting up the system in Step-Servo QuickTuner in some detail before we switch over to Studio 5000 for Ethernet IP specific parts. So if you want to learn about the Absolute Encoder, but you aren't using Ethernet IP, you are still in the right place. Now, if you're familiar with Applied Motion Products and Q programming and configuration in general, you probably already know that the easiest way to configure your integrated motor is through the built-in configuration software. In this case, I'm using a TXM24X3B-IP integrated motor, which has the TruCount encoder in it, and that's configured with the Step-Servo QuickTuner software. We'll go through that method first, and then we'll switch over to Studio 5000 and do some absolute moves from the home position we set in Step-Servo QuickTuner, and I'll also show you how to reset the Absolute Encoder position and limits directly from Studio 5000. Okay, if you'd like to follow along, the Absolute Encoder setup is outlined in App Note 52, which can be found in the support section of our website, appliedmotion.com. As with the previous videos, the AOIs I'll be using can be found under Application Note 46, also on appliedmotion.com. The input and output assemblies are detailed in the Ethernet IP appendix of our host command reference, which can be downloaded at appliedmotion.com/HCR, and the EDS file for your particular drive can be found under Downloads on the drive's product page. Okay, let's take a look at the specs of the Absolute Encoder so we can remember what we're dealing with here. So this is a multi-turn, batteryless, magnetic Absolute Encoder. What that means is there are no gears internally to wear out, and there's no batteries internally to replace. So you don't have any sort of mechanical maintenance from the gearing. You also don't have any electrical maintenance because the batteries are never going to wear out in this because they don't exist in this. That has another advantage too, where you can actually leave this thing powered off forever and it will never lose position because there's never a battery that's going to eventually run out. So really, you have ultimate confidence in the positional accuracy being retained power cycle after power cycle with this TruCount encoder. We have a 16-bit turns counter, so that allows us to track 65,584 turns before rollover. And we have 15-bit single turn resolution, which is 32,768 counts per turn. Although we have set the default to 20,000 counts per rev to match our existing Step-Servo motors. And finally, we've got a positional accuracy of 0.09%. Now let's take a look at our hardware. Here I have our TXM24X3B-IP connected to an old rod-style actuator that I had laying around the office. The TXM24 series with the M12 connectors is IP65 rated, and as it happens, this actuator is as well. So I've actually got a complete industrial washdown actuator solution here. And as we zoom in here on the output, you can see I've got my handy Applied Motion Products screwdriver, and I've also got some engineering graph paper. And we're going to use this handy Applied Motion Products screwdriver as our marker. So for this demo, I want to move the actuator out and in across this graph paper. My paper here has 5 divisions per inch. You can see these major divisions are 1 inch apart. The minor divisions are 0.2 inches apart. So we want to set up electronic gearing to make my move calculations easier. So let's say 10,000 counts per inch. So 10,000 counts of the motor will get me from here to here. So let's sort of graph this out on the paper. So let's say I want my home position to be on this division right here. That's going to be my home. And then my major divisions here are going to be 1 inch apart. And then let's say on this end here, I'm going to call this my clockwise limit. And on my actuator, I should mention, clockwise is this direction, counterclockwise is that direction. And so over here, I will do a counterclockwise limit. And let's just pretend I've got some sort of a hard stop here and some sort of a hard stop here. So with this configuration, I want my home position to be in, near my most retracted state. I want to have a little bit of buffer behind that position. So you can see I have two divisions past my home position. So I don't usually go over here in my application, but sometimes I might. Generally, I'm going to be working in this range. So this is my 0 position. This is my 1 inch extended position, -2 inches, or I'm sorry, +2, +1, -1, -2, -3, -4. And if I'm using 10,000 counts per inch, I just need to multiply my position, my desired position, by 10,000 to get my distance. So this is what we want to design our system to look like. And then we'll drop our linear actuator back on here, and we'll deal with homing it out a little bit later. As part of commissioning this system, we need to do the standard configuration and tuning. That is, the same for any Step-Servo motor. We need to define the electronic gearing. So that's going to convert whatever the existing electronic gearing resolution of my linear actuator and motor combination is into something useful so I can take advantage of this 1 inch graph paper and move cleanly from inch marker to inch marker. Then I need to define the home position, which we've got on our paper laid out where we want it to be. And then finally, we need to define the end of travel limits. And so those are the software limits that are going to be burned into the motor to say, okay, never exceed this point or this point. And then finally, we're ready to start moving. So let's tackle electronic gearing first. Different lead screws have different number of turns required to produce 1 inch of linear motion. So we need to calculate the electronic gearing required based on the lead screw spec. My linear actuator has a lead screw that gives me 4 millimeters of motion for every revolution of the motor. But I like inches, my graph paper's in inches, my programming units are going to be in inches, so we got to convert that to inches. So 4 millimeters is 0.15748 inches. And we have a native resolution, you'll recall, of 20,000 counts per rev. So that gives us a native electronic gearing of 7.847 times 10 to the -6 inches per count. That's not in any way, shape, or form a useful number for us. We want 10,000ths of an inch per count. So we can rearrange that equation to solve for counts per rev, and that gives us 1574.8 counts per rev, or approximately 1574. So let's talk about that error on the bottom there. There's two things going on. The first is that because we have a metric lead screw and we're using imperial programming and configuration units, we're going to have a mismatch. You're not necessarily going to end up on a nice clean number. So it's pretty important to run through this exercise before you pick a lead, before you settle on a lead screw. Make sure that it's going to match and it's going to give you a nice integer for electronic gearing. The other thing you might notice is that I rounded down to 1574 instead of up to 1575, which is technically closer. So by doing that, I actually increased my error from 0.2 counts per rev to 0.8 counts per rev. Why did I do that? I did that because the electronic gearing in our drive needs to be set in even numbers, right? So 1575 is not a valid counts per rev setting. It has to be 1574 or 1576. So all that said, I am going to end up with an electronic gearing of 1574, which is going to give me almost 10,000 counts per inch. I'm just not going to be off by 0.8 counts. And we're only going plus or minus a couple of inches here, so we're never going to notice that in our application. In your application, you might notice it. And that's why it pays to do this exercise first to make sure you land on an even integer number for your electronic gearing. Let's actually look at how you run this thing. The first thing we're going to do, actually before anything else, is we're going to connect to our motor. So my motor's already here, it's powered up. Hit the ping button to talk to it. Yep. And you can see over here in the monitor, I'm getting values coming back. That's a good indication that's working. I've got an encoder position here, doesn't really mean much now. So the first thing we're going to do is we're going to set our electronic gearing. So remember, the number we came up with was 1574. 1,574 steps per rev. Notice it says power cycle is required after electronic gearing change. So we're going to download to the drive. It's going to warn us. We're going to reset the software limit. We know that. We're good. And then as soon as it's done, 1574. We're going to power cycle as requested, or as required, I should say. So I'll turn off the drive and you'll see the screen go black there, or go blank, disconnected. And then I'll turn the drive power back on. Ping it. Oh, it's alive, it's awake. Connect. Upload again. And there we go, 1574. So let's give this a try. Let's go over to our motion simulation tab, and we'll turn on our motor view here. So we can see our motor is, our actuator rather, is sitting with the screwdriver sort of pointed in between some numbers. So let's jog it. Let's go 1 RPS, and let's go counterclockwise. Oh, there we can see it move. And clockwise, there we go. Okay, so let's try to land somewhere about on the, let's actually go for the home mark. So we're going to slowly adjust our motor until we get to the home position that we want to set. That looks like it's just about dead in the middle of that Sharpie mark. So now that we're happy with the home position, we're going to set it. We're going to burn it into memory. So go to Tools, Set Home Position. And this is a warning telling us again that the software limits are going to be reset. We know that. That's why we're doing things in this order. We set the electronic gearing first, then we set the home position, then we set the limits. Always do it in that order. And then this question is, do you want to set this as current home position? That's what we're here for. Okay, we're good. This is now home. So we know these are 1 inch apart. We know our motor is set up for 10,000 counts per inch. So it should be that if we tell the motor to go negative 10,000 counts, do a relative move, we should see it move from home to -1. How about that? What if you want to go only half of an inch? -5,000. Right in between the two. So let's move back to our home position. Move to home. And now we're good. So now we'll work on our last step of the process, which is setting up the limits. Limits are set up in the Tuning and Sampling tab, so we're going to go over here. Now, let's just walk through exactly what we're looking at here. So to set the limits, you jog the motor to the limit position, and then you use the flag to set it. So we're going to jog using this information. So jog speed 1 RPS, accel decel 10. Let's go a little higher than 10, so I'll go 100. So let's do the counterclockwise limit first. So I'm going to hit the checkbox that says, yes, I want to use this limit. And I'm going to use these arrow keys here to jog. So I'm just going to hold this down until we hit our counterclockwise limit. And of course, we can overextend this because the limit's not set yet. So now we're going to back up, and we're just going to kiss that Sharpie line. That looks perfect. So now that our counterclockwise limit is set, and you can see it's -4520. So it's just a little bit further than right dead on the 4-inch mark, which is exactly what we want. We want a little bit of overshoot allowed. Because remember, this is a software limit. we're saying that our mechanical hard stop is this line over here. So there's plenty of buffer here between the counterclockwise limit and the mechanical hard stop. So now that that is set, we're going to move over to the clockwise limit. We're going to check to say we want to use it, and we're going to use these jog buttons to jog back over to the clockwise limit. And this is going to be way too slow. So let's bump that speed up. And now that we're close, we can dial the speed back down. And remember this, we want this to be just on the other side of the +2, the positive 20,000. So 20,409, that looks great. So these checkboxes are both checked. The limits are both set in the correct text box. Checkboxes, let's hit set limit. This is an important note. Right now, these are volatile limits. And this checkbox is telling us if you want them to be non-volatile, which we do in this case for the Absolute Encoder, we need to download them to the drive. So we're going to download all to drive. Okay, now we're good. Our limits are set. You can see here, if we play with these jogging buttons, you can watch the approximate position of the motor and the load relative to the limit switches. Just kind of a cool little feature. All right, let's go back to the motion simulation tab and let's move to home. And we can do some absolute moves. Let's do negative 1 inch moves. Let's do absolute. And then of course, if we hit absolute move again, it's in the same position already, so it's not going to move. But let's move 1 inch further. We can do that with a relative move, relative 10,000 counts. Relative 1 inch. And then we should be able to hit this -4 mark because our counterclockwise limit is on the other side of it. So we'll do 1 inch, no problem here. But let's go one more. Let's try to accidentally do another 1 inch move, which will put us dangerously close to that hard stop. Let's see what happens. Oh, it stops. And it tells us there's an alarm. It's yellow, so that's a warning. We're going to go to the alarm tab, counterclockwise limit. So let's jog just a bit clockwise, get off of the limit, warning goes away, drive's happy. And just for fun, let's go to the other direction. Let's go home. And then we'll set up, let's just do a 50,000 count move in the clockwise direction, which should put us, well past our physical hard stop, but we're counting on that soft limit to stop us. Oh, and indeed it does. Clockwise limit. We'll jog counterclockwise off of it, and we're good to go. So this is it for configuration and setup. Our drive is now ready to go. It has the limits and the home position and the electronic gearing burned in and ready for our application. So we're going to switch over to Studio 5000 and take a look at how we might use this in Compact Logic. Okay, here we are in Studio 5000. So just like in the last video, I'm not going to run through exactly how to set all this up. Suffice to say, I grabbed the EDS file for the TXM24 off of the appliedmotion.com website. I installed it with the hardware installation tool, so you can see down here on my network, I have a TXM24 named TXM24X3BIP, which is the model number of my device, and it's talking on the network. So I have my input assembly AOI. I'll just run through real quick. My input assembly AOI, alarm code, status code, jog move, stop move, relative move, absolute move, motor enable, motor disable, alarm reset, and SCL command execute. So I want to start by going through and doing a couple of move commands using the Absolute Encoder. So I'll turn back on my hardware view here. All right, so we see that the drive is online because we see the input assembly moving around a little bit. That's always a great clue to know, is the drive actually talking or are you seeing stale values? And also down here, if we look in the EtherNet network, there's no little error icon next to the TXM24. So we know we're good, we know we're talking. Status code tells us the motor is enabled. the motor is in position. That's all great. If we look at the hardware view, though, we can see the motor is at just sort of some random spot along the line. So the first thing we'll do is let's move that back to the home position. So let's go down to our absolute move AOI. We're going to set up some parameters. I want my distance to be 0. That's going to be my 0 position, my home position. And velocity of 2, that's fine. Acceleration, deceleration, both 100. That's just fine. So I'm going to start off this move. And I should land right on the home position. Perfect. Let's do a couple of relative moves. Let's say I want to move to the 1-inch extended position. So I'm going to program a relative move AOI block to negative 10,000 because I'm at position 0 now. So I'm going to do a relative move to negative 10,000. Velocity of 2. Okay, let's bump that up to 4 just so we can see the difference in speed when we do a relative move and an absolute move. So a little bit faster there, moved over to negative 10,000. Let's do another relative move to negative 10,000, and this should put us at the 2-inch extended mark. And then we can do an absolute move, I don't know, back to, let's call it negative 12,000, which should put us right on one of the minor division lines. So you can see we landed here right on this minor division line, one minor division between negative 1 and negative 2. And remember, this is 5 divisions per inch graph paper, so that is exactly where it should be. So really, now that we are back in Studio 5000, we've done all of our configuration and setup in Step-Servo QuickTuner, there's really not a whole lot to show here because now this works exactly like a standard product, except that it remembers a position after power cycles. So let's talk about these software limits and how they're going to actually help protect us. So let's say if I do a jog move, and that's covered by my hardware view, so I'm going to move this around a little bit. Let's just put that up in the corner there. So I'm going to kick off a jog move, and I'm going to go in the negative direction, which is towards the counterclockwise limit, 1 RPS. And let's say I kind of forget what I'm doing and I walk away from the machine. I don't tell it to stop. I am counting on this TruCount encoder remembering the counterclockwise limit and stopping the motor for me. So let's see if that happens. Perfect. The motor stops. Let's take a look at our status code AOI. Oh, it says motor enabled, in position, alarm present. So we have an alarm. Now let's dig in a little bit further and see what that alarm actually is. If we go over to the alarm code AOI, we can say, hey, we're at the counterclockwise limit. Exactly what we should be. So let's jog a little bit in the other direction, in the positive direction. And I'll stop the motor. And enabled, in position, in the status code, no alarm present. And indeed, there's no alarm. It clears itself when you back up off of the limit. All right, that is really just about all we can show here. There's really not much more to it than that. It uses the same AOIs as the incremental encoder versions, and the difference is that it maintains position. So let's look at that. Let's pull the power. Remember this position number. We are at negative 36951. So we're going to pull the power, and we're going to be able to tell that the power is pulled because that AOI block is going to stop refreshing. The input assembly is going to stop refreshing, and we're going to see an error down here on the TXM24 EtherNet device. You see that little yellow triangle with an exclamation mark in it. So now we've stopped refreshing. You can see this data is stale. It's not moving anymore. So I'm going to plug the motor back in. It'll take a moment to come back online. And then as soon as it does, this error bar is going to go away, just did. This is going to start refreshing, and look, the position stays the same. So we are good to go here. So let's move back to our home position. We're going to go to absolute position 0. And now we're going to talk about what if you want to change things around. So let's say I want to, for whatever reason, change my application so that my home is going to be a little bit more in the center instead of biased off to one side. So in red here, I'm going to mark my new position. So I want this to be my home, and I want to actually change my limits too. So this is going to be now my new +1, +2, and limit. And then this will be my new -1, -2, and counterclockwise limit. So how do we do that? That's why I've imported this SCL command execute dialog box down, or AOI down here. So if you open up app note 52, it'll walk you through all this. I'll just do it, by voice here. So the first thing we're going to do is we're going to move to what we want our new home position to be. So we are going to do an absolute move to, we can see here, this is our new home position. Currently it's at -1. So we're going to go to -10,000. Send that over. All right, so now our motor is in what we want to be our home position. And you can see -10,000 up here in the encoded absolute positions. So we are going to give this a SP0 and an EP0. So to do that here, I'm going to do a single quote, capital SP, and single quote, hit enter, and that'll convert that automatically in Studio 5000 into the decimal equivalent. And then we're going to do 0. That's the first parameter. That's what we want. We're going to send it. And we're going to do EP, again, 0, send. Yeah, that was my mistake. So to make this work, you need to do it in the right order. So you need to do the EP0 first and then the SP0. And then these will both reset to 0. So now we're good to go. And now we can see if we do another absolute move. We haven't changed this block at all. Absolute move to position -10,000. And before, we were on these black marks, so -10,000 was here. And now we're on the red, so it should move to this line right here. Let's give it a shot. How about that? Works just as expected. Okay, so let's move to our new position. I'm sorry, that's a mistake. This is -2. Let's move to our -20,000. And this, remember, is where we want our new counterclockwise limit to be. So we're actually going to move a couple of counts beyond that. Let's go 2,500. And now we're going to set the counterclockwise limit. So to do that, we're going to use the LM command. Oh, and I'm realizing I don't actually have to move the motor at all. So I know, so here, let's move back to our home position. You can do this either way, but just for clarity. Move back to our new home position, which remember is the old -1 position. Perfect, right there. So now, to set our limits, we use the LP and LM command. So the positive is the clockwise direction, and the negative is the counterclockwise direction. So let's do our clockwise limit a little bit after this. So we want this to be, let's call it 2,500, and the counterclockwise -2,500. 20,500, that is. So we're going to go down here, and in the command letters, we're going to do LP for the positive or clockwise limit, and that's going to be 20,500. And we're going to send that along. And we're going to do an LM of -20,500. And we're going to send that along. Now our limits should be set. So let's just do a jog move here. Let's jog at 2 RPS. So this will go in the clockwise direction. And now, instead of seeing the limit trip here, we should see it trip here. And there we go. Now we'll go in the negative direction and just, oops, sorry, I want -2, not -20. And we'll just make sure that my limit is set correctly in the counterclockwise direction. Perfect. Now, let's go to absolute position 0 again. We'll move a little faster. Perfect. Okay, so now I'm going to power cycle the unit. Let's see what happens here. So notice absolute position 0. Unit is power cycled. And watch it come back online. Oh no, we're back to -10,000. We're back to our initial time or our initial position line. That's not great. Why did that happen? That happened because we did not save the values. So we can make all the changes we want, but until we send the SA command, the save command, they're not going to be saved in non-volatile memory. They're going to remain volatile numbers. So let's go through real quickly. So we are at what we want to be our new home position. So we're going to send EP0, and we're going to send SP0, and we are going to send LM -20,500, and we are going to send LP +20,500. And now what we did not do last time, we are going to send SA with no parameter, 0. We're going to send that, and now let's just do a couple of quick checks to make sure we're on the right page. So we're at our new home position, and we can see that we are at absolute position 0, so we know the home position took. And let's just jog and see if our limit switches took. We're going to hit right here, and if not, we're going to hit right here. Oh, okay, so our counterclockwise limit is good. And let's go in the other direction. We're going to do +4. And again, we should stop right there. Perfect. All right, and so let's just give ourselves a absolute move back to position 0. Our new home. Okay, now we're going to cycle power. And when we come back online, we should see that position should remain 0. Remember last time it switched back. Position should remain 0, and the limit should stay in non-volatile memory. So the position stayed at 0, so we're good there. And let's just do another quick jog to make sure that our limit's also stuck. Perfect. Other direction. And that looks great to me. So I think we are good here. I think this is just about everything that you'll need to do to get your Absolute Encoder specifically running up in Studio 5000. So the AOIs I use can be found in the support section of our website, appliedmotion.com, under Application Note 46, and the Absolute Encoder setup document can be found in the same place under Application Note 52. If you'd like more detailed information about our Ethernet IP implementation, input and output assemblies, etc., the Ethernet IP appendix of the host command reference is always the best place to start. You can find the latest version at appliedmotion.com/HCR. In future videos, we'll be exploring things like adding multiple drives on a network and manipulating I/O and decoding I/O on the drives. And if you've got any questions about AOIs, Ethernet IP communications, or motion applications in general, please reach out to our applications engineering team through our website at appliedmotion.com, email us at support@appliedmotion.com, or just give our apps engineers a call at 800-525-1609. Thanks for watching. I hope this was a useful video. If you have any other topics you'd like to see covered, please leave them in the comments below or let our apps engineers know when you talk to them.